Take a look around. Don't be alarmed, but you are surrounded. They're in your pillows and walls, in your clothes and in your body. There is no escape. Chemicals are everywhere and in everything. Some are harmful, while the vast majority are essential building blocks for things like plastics, clothing, fuel, and medicine. Their ubiquity gives rise to a synthetic chemical industry that contributes $5.7 trillion to global GDP, supporting 120 million jobs. Now, a simple but powerful type of catalyst is making waves by driving down the cost of synthesizing some of the most difficult chemical structures. Join me as I explain asymmetric organic catalysts, what they are, how they work, and why they are a 2021 Nobel Prize winning innovation. Chemicals, also called molecules, come in many shapes and sizes, and it is their precise structure that gives them their unique properties. Organic molecules, which are made from carbon, oxygen, and hydrogen, are some of the most complex and interesting structures found in nature. Making these organic molecules is big money. Your friendly neighborhood drug dealer, the pharmaceutical industry, specializes in making complex organic molecules to treat diseases. In the highly regulated pharmaceutical industry, drug purity is extremely important. Long, multi-step synthetic chemical reactions will produce a small amount of drug molecule. They will also produce many unwanted byproducts that need to be removed. Many of these byproducts have distinct differences in their shape, size, or charge. These differences can be exploited to separate them from the desired molecule. However, there is one type of byproduct that is almost impossible to remove: the enantiomeric byproduct. The enantiomeric byproduct, or enantiomer, has exactly the same shape, size, and charge as the desired molecule. The only difference is that the structure of the enantiomer is a mirror image of the desired molecule, such that it is impossible to superimpose the structure of an enantiomer over its mirrored twin molecule. This is very similar to how it's impossible to superimpose your left hand over your right hand, no matter how much you twist and turn it. It's important to note that not every molecule can have an enantiomer. Symmetric molecules do not have enantiomers because their mirrored twin molecule can be superimposed over the original. In other words, they are the exact same molecule. Only asymmetric molecules can have enantiomers. Their mirrored twin structures cannot be superimposed over each other. If enantiomers are so similar to active versions of drugs, then why are they so bad? Well, despite having the same shape, size, and charge as the active version of a drug, an enantiomer of a drug can behave very differently to the active version of that drug. The 1950s drug thalidomide is a devastating example of the dangers of enantiomeric byproducts. Thalidomide, containing a mixture of both the active version of the drug molecule and its enantiomeric byproduct, was prescribed to pregnant women to treat nausea. What followed was the largest human-caused medical disaster ever. Over 10,000 infants were born with severe limb and birth defects, with an infant mortality rate as high as 40%. Countless others did not survive pregnancy. Scientists determined that the enantiomeric byproduct in thalidomide was to blame. To ensure this never happens again, regulatory agencies now require stringent safety and efficacy tests for drugs to come to market, especially for drugs that contain an enantiomeric byproduct. When developing pure asymmetric molecules, it's practically impossible to remove enantiomeric byproducts from a chemical mixture. The best solution is to not produce the byproducts in the first place. Scientists take advantage of catalysts that select for one version of an asymmetric molecule over the other. These rare catalysts are called asymmetric catalysts, and they are the holy grail of synthetic chemistry. Asymmetric catalysts fall under three main categories: enzymatic catalysts, metal catalysts, and organic catalysts. Enzymatic catalysts are large and complex protein-based catalysts. Made from a string of amino acid building blocks, these enzymes are found in all cellular life. They catalyze the breakdown and synthesis of molecules essential to life. To produce drugs, a pharmaceutical company will often take a natural biological enzyme with a known catalytic function and reproduce it to catalyze the same chemistry on a larger scale. Enzymatic asymmetric catalysts are very expensive to use but they are stable and non-toxic. Metal catalysts are small and simple. They take advantage of highly reactive transition metal elements. However, the high reactivity and simplicity comes at a cost. Most of these catalysts are only stable in air and moisture-controlled environments. If you leave them out on a benchtop, you're gonna have a bad time. These metal catalysts are cheap, but dangerous and toxic. Organic catalysts are small organic molecules, very similar to the amino acid building blocks that form the structure of enzymatic catalysts. These organic catalysts can't facilitate as many different kinds of reactions as enzymatic or metal catalysts, but they are extremely cheap and very stable, making them readily available and easy to use. Benjamin List and David Macmillan, the 2021 Chemistry Nobel winners, helped popularize organic catalysts in synthetic chemistry. In 2000, they showed that organic catalysts could perform asymmetric aldol and Diels-Alder reactions, two important reactions typically performed using enzymatic or metal catalysts. Use of organic catalysts has expanded since those initial findings. Now you may be wondering, if these organic catalysts are so impactful, why did it take so long for these scientists to win the Nobel Prize? And that is a very good question. It's likely that the Nobel Prize Committee have been waiting for clear, real-world impacts from the discovery before awarding the Nobel Prize for organic catalysts. Because of their simplicity, cheap cost, and ease of use, organic catalysts are now widely used in academic chemistry labs to identify potential new drugs. In the pharmaceutical industry, the antidepressant paroxetine and antiviral oseltamivir are now being produced using organic catalysts. However, the pharmaceutical industry still largely utilizes metal catalysts and occasionally enzyme catalysts to produce asymmetric molecules. This is probably because economies of scale and profitable, very profitable, drug contracts pay for the infrastructure to work with dangerous metal catalysts and expensive enzyme catalysts. List and Macmillan's research has expanded our chemical toolkit of asymmetric catalysts, providing massive real-world benefits to humanity worthy of Nobel Prize recognition. While organic catalysts may not be the hottest new technology, their slow burn is helping to usher in a brighter future, a future with more drug treatments and fewer diseases. I'm Chad Hicks. Thanks for watching.